In the last video, we came up with an integration technique which undoes the chain rule. This was called substitution. In this video, we're going to find an integration technique which undoes the product rule. To begin, let's look at the product rule for differentials. If u and v are two functions, say with variable x, then what is the differential of their product? Well, the product rule says it's u dv plus v du. Okay, well then what happens when you integrate both sides? Since integration undoes differentiation, the integral of the left side is just going to be uv, while the right side is just integral of u dv plus integral of v du. Okay, there should probably be a plus c, but both of these indefinite integrals would involve a plus c as well, so we're just not going to worry about that plus c. Next, we're going to rearrange terms to get integral of u dv equals uv minus integral v du. This is called the integration by parts formula, and you should definitely memorize this. Now, what's so good about it? Why do we care about this formula? Well, it's useful when we're trying to compute the integral of a product of functions. The idea is that we can replace this integral with this integral, hoping that it's a little easier. Now, why wouldn't we just compute the integral of a product of functions one factor at a time? The answer is because it's not correct. It was not correct for differentiation. You needed the product rule there. And it's not correct for integration. We need integration by parts for this. So, for example, the integral of x cosine x dx is not just the integral of x times the integral of cosine. So, how do we do this integral? Well, we use integration by parts. What we do is we let u equal some part of the integral. I've chosen x, and dv will be the rest. So this is going to be the integral of u dv. And these are the choices that I've made. I'll explain how these choices are made in a second. But for now, let's now compute du and v. Du will just be computed the same way we computed du when we were doing substitution. Just take the differential of both sides. Whereas v will have to be computed by integrating both sides. So let's do that. Du is just dx, and v is the integral of cosine x dx. But we don't put a plus z here. Next, we write down what the integration by parts formula says. The integral of u dv is equal to uv minus the integral of v du. And now you'll notice that this integral, which remains to be computed, is easier than the original integral, and so we can just compute it. Now, how do we pick the u and the dv? This acronym helps you to make this decision. ILATE. It stands for inverse trigonometric functions first, logarithmic functions next, algebraic functions, then trigonometric functions, then exponential functions. Higher up on the list means that you're more likely to make that your u, and lower down on the list means you're more likely to be dv. By the way, what does algebraic mean? That means any kind of polynomial, any kind of fraction or square root, any expression which can be expressed using multiplication, division, addition, subtraction, and raising to constant powers. Let's do an example. How do we evaluate the integral of natural log of x? Well, let's see. This isn't a product of functions, at least it doesn't look like it. But if I'm clever, I can see that actually it is a product of functions, natural log of x times 1. So let's use the ILATE acronym to see what substitutions we should make. Natural log is a logarithmic function, and 1 is algebraic, and therefore u should be the logarithmic function. That was higher up than algebraic. And so dv should be just the remainder of the integral. In this case, it was just dx. Okay, then let's take the differential of both sides to find du, and let's integrate both sides to find v. So du becomes 1 over x dx, and v is just x. Again, we don't put the plus c here. Now the integration by parts formula tells us that the integral of u dv is equal to uv minus the integral of v du. Again, everything's color-coded here so you can see where everything belongs. And now this new integral can be simplified, right? X cancels with x, and so this is just the integral of 1 dx. Alright, so we can do that integral. It's just x. And now we're going to evaluate from 1 to e. So first plug in e, and then plug in 1, and subtract, and simplify. Natural log of e is 1. Natural log of 1 is 0. So this is, let's see, that e cancels with that e, that's 0, and then minus negative 1 is 1. Now in some cases you are going to have to solve for the integral algebraically after applying the integration by parts formula. As an example of this, let's try to compute the antiderivative of secant cubed of x dx. Well, let's first note that this is secant squared of x times secant x. And I want to use integration by parts to evaluate this integral, but notice that both factors are trigonometric, so the ILATE acronym doesn't work. So instead, I'm just going to use the fact that I know how to integrate secant squared, because it's one of the basic integrals that we've memorized. And so I'm going to make that my dv, and hopefully letting u equal secant x will work. Let's find out what happens. Let's let u equal secant x, and dv is secant squared x. Then we integrate both sides to get v, and that'll be tangent x, and then take the differential of both sides here to get your du. And that's secant x tangent x dx. Now let's apply the integration by parts formula. Let's simplify now, combine these two tangent x's. And now what I'm going to do is notice that I haven't really exchanged my tricky integral with an easier integral, at least it doesn't look like it. However, I can use a trigonometric identity. I do know that tangent squared x is equal to secant squared x minus 1. This is just a trigonometric identity that you learned years ago. Okay, but now what we can do is rewrite this integral. Right? Let's distribute this secant x to both terms. Notice that this minus cancels with this minus to make this plus. And what do I see? Now I've got this integral of secant x, which we computed in a previous video, I believe, and this integral is appearing again. This is the one we started with. So at this point, what we're going to do is write this full equation and basically solve for this integral algebraically. We're going to add this integral to both sides. And I get 2 times this integral that we want to compute is equal to secant x tangent x plus, okay, here's the formula for the integral that we came up with, and here's our plus c. So now to finish computing this integral, we just divide by 2. Sometimes we do need to use integration by parts more than once. Okay, here's a good example of this. This is a product of two functions, e to the x and sine x. So let's see, which function should be u and which should be dv. ILATE says that the exponential function should almost always be our dv, right? It's the last in the acronym, and trigonometric comes before exponential. So let's make the trigonometric function our u, and let's make dv equal to e to the x dx. Then take the differential both sides here and integrate both sides here. We get cosine x dx, and here we get just e to the x, and again not putting plus c here. Now the integration by parts formula says this. Okay, now how do we compute this integral? It doesn't look any easier than the original integral. It looks about the same level of difficulty. But here's a case when we have to do integration by parts a second time. We're going to use the trigonometric function as our u again, and we're going to use the exponential function as our dv again. So these are the choices we make. Let's take the differential of both sides here to get negative sine x dx, and on the right we integrate both sides. Okay, now the integration by parts formula says that this integral is going to be uv minus integral v du, and let's simplify. This negative cancels with this negative, but this negative then distributes to both terms, so that's why we have both negatives here. And so what I see is this integral appearing on the left and right again. So let's solve for it algebraically. Add this integral to both sides, and then divide by 2. And here's our integral. Now there is such a thing called the tabular method. If one of the functions happens to be a polynomial, then there happens to be a shorthand for applying multiple iterations of the integration by parts technique without doing too much writing. You don't have to pick the u and the v each time. However, I don't plan to teach this because it's just not useful in instances unless one of the functions happens to be a polynomial. So if you're interested in learning this, just look up tabular method on Google or something. To recap, we now have our third integration technique, and it's called integration by parts. We have to make a choice of a u and a dv, and we use the acronym ILATE to make these choices. Now, you may need to solve for the integral algebraically, and or apply the integration by parts multiple times. This is not uncommon. In the next video, we're going to come up with a few more integration techniques. But before we do so, you now have the tools to compute this antiderivative, so give it a go.